Good afternoon, students. Welcome to CEC Live Lecture. In today's session, we have with us Dr. Aparajita Chauhan. She is an Associate Professor from Sri Aurobindo College, University of Delhi. Today, she will be discussing on the topic of Aldehydes and Ketones, Part 3. Before we begin, students, I would like to tell you that if you have any query, feel free to contact on the toll-free number 1800-110-430. So let's begin, students. Welcome, ma'am.
Thank you, Inaya. So today we'll be talking further on aldehydes and ketones. In our previous lectures, we have done the nomenclature of aldehydes and ketones, their methods of preparation. Today we shall be continuing with methods of preparation only, but we shall be discussing those methods which are specifically used for preparation of aldehydes and then which are used for preparation of ketones. Theoretically, we can prepare aldehydes from acids by their reduction. But if we talk of it practically, it is not possible, because when we do the reduction of carboxylic acid with lithium aluminium hydride, we will get an alcohol, since lithium aluminium hydride is a strong reducing agent. So what we can do now is we can convert these carboxylic acids into their acid derivatives and do their reduction. So the first method of reduction in which I will be interested in discussing is Stephen's reduction of nitriles. So what we do in Stephen's reduction of nitriles is we treat alkyl cyanides with stannous chloride and hydrochloric acid. Stannous chloride and hydrochloric acid reacts to form H2CN SnCl4. So when we are using stannous chloride and we are getting SnCl4, what we observe in this reaction is that Sn is being oxidized, that is, its oxidation state is changing from +2 to +4. That means it is giving 2 electrons. Where are these 2 electrons going? These 2 electrons go to this carbon, and this double bond becomes, this triple bond becomes a double bond. That it goes to, the pi electrons go to nitrogen. As a result of which, the hydrogens add to carbon and nitrogen, resulting in formation of an aldeamine hydrochloride. And now this aldeamine hydrochloride on hydrolysis will give us a aldehyde and ammonium chloride. So what we find is that the reaction will stop at aldehyde and it cannot be reduced, aldehydes cannot be reduced further to alcohols. We can also bring about reduction of nitriles with another reducing agent, which is BAL, and which I'll be discussing later on. So now if we go on to next reduction reaction, that is we can prepare aldehydes by reduction of acid chlorides. What we do in this reaction is we take vapors of acid chloride with hydrogen gas and they are passed over palladium. But we know palladium is a very good catalyst, and if we do this reaction, then we would simply get an alcohol. Now we want to get an aldehyde. So what do? We poison palladium with barium sulfate. Barium sulfate has less surface area, as a result of which the reduction will stop at the aldehydic stage and the aldehydes will not be able to reduce further to alcohols. So what we find in this is that when we do the reduction in presence of palladium poisoned by BaSO4, then what we observe in the reaction, then in the reactant if we find it is acid chloride, then the Cl is being replaced by hydrogen in aldehyde. So what we can say is simply what is happening, that hydrogen is reacting here, one atom of hydrogen is removing Cl to form hydrochloric acid and the other hydrogen is replacing this Cl. So what we are replacing in this reaction is reduction reaction. We are replacing this Cl with a hydrogen here, getting a aldehyde. Now we know that PDBaSO4 is also known as Lindlar's catalyst. So in this it is not shown, but here we have a triple bond. So if we have a triple bond in the molecule and then along with that we have an acid chloride, what we can do is we can prepare an unsaturated aldehyde having a double bond. We know when we do the Lindlar's catalysis or Lindlar's reaction, what happens in that case is that hydrogen adds across the triple bond cis. That is, both the hydrogen atoms will add from the same side of the triple bond, resulting in a unsaturated aldehyde like this. So when we are using Lindlar's catalyst, we are not able to reduce this completely to a single bond, and we will get an unsaturated aldehyde here because palladium has been poisoned with BaSO4. The next reaction is that we can prepare aldehydes from carboxylic acids by reduction with lithium aluminium hydride. But is it feasible? Practically, it is not, because lithium aluminium hydride is a very strong reducing agent. I can say it is like a charging bull. It would reduce the aldehyde formed to a alcohol because aldehydes are more susceptible to reduction as compared to acids. So how can we stop this reaction at the aldehydic stage, or how can we circumvent this problem? What can we do is that since acids, we can convert acids into acid chlorides or esters. We know acid chlorides and esters or cyanides are more susceptible to reduction as compared to carboxylic acids. And then what we can do is we can use a milder reducing agent, that instead of lithium aluminium hydride, we can use a reducing agent which is bulky. So what do we do in this is that first what we are going to do is that the milder reducing agent that we can use here is lithium aluminium tri-tertiary butoxyhydride. So if you compare lithium aluminium hydride with lithium aluminium tri-tertiary butoxyhydride, what we find here is that with lithium aluminium hydride is a smaller reducing agent. There is no steric hindrance. But when we talk of lithium aluminium tri-tertiary butoxyhydride, then what we find here is that it is a bulky reducing agent. So when we have a bulky reducing agent, the reaction will stop at an aldehydic stage. Second, what we find is now what we can do here is we can convert the carboxylic acid into acid chloride. Why are we doing this? Because in acid chloride, the reduction of acid chloride is easier. So we can use here a milder reducing agent. That is, we can use lithium aluminium tri-tertiary butoxyhydride here instead of lithium aluminium hydride. Please remember, if we were using lithium aluminium hydride even with acid chlorides, then acid chlorides would also be reduced to alcohol. We will not be able to stop the reaction at an aldehydic stage. So first what we are going to do is we are converting acid into acid chloride by reaction with thionyl chloride. Now what we do in the next reaction is we do the reduction of acid chloride with lithium tri-tert butoxyaluminium hydride. When this Cl is replaced with an hydrogen here, and what we get here is an aldehyde. How does this reagent work? So what we find here is this brings about nucleophilic reduction. That is, in this case, lithium is positive, aluminium has a negative charge on it. So what aluminium does here is a hydride is shifted from here and it goes and attacks the carbon here. So first what is happening is that this lithium reacts with oxygen here to form, and this oxygen now becomes electron deficient. Since it becomes electron deficient by forming a bond with lithium here, it will pull electrons from here. This acts as an electrophile. This oxygen is acting here as a nucleophile. It forms a bond with lithium. Now what happens in the next step is that this hydride from here is attacking on this carbon here. So this is a nucleophilic attack here, and now what we have here is that this carbon is attached to these groups, to a Cl and an oxygen. Now the question arises, what will leave from here, whether it will be Cl or an oxygen? Then we know that Cl is a better leaving group as compared to oxygen. Then this Cl along with lithium is eliminated off as LiCl, and these lone pair of electrons go back into the ring, forming a double bond. So what we can say here is that because this in acid chloride, this C is electron deficient because it is attached to a more electronegative oxygen here, or we can say that this oxygen pulls the electrons towards itself, as a result of which it forms a bond with Li+, and this hydride ion from here goes and attacks the carbon here, resulting in this intermediate. Then this intermediate loses LiCl, resulting in formation of an aldehyde. Now if you look into the structure of this tertiary butyl aluminium hydride, so what we find is that this reagent is bulky. Whereas if you talk of lithium aluminium hydride, then in lithium aluminium hydride, that is a small reagent. Secondly, this molecule has only one hydride which it can shift. So since it has only one hydride which it can shift, so we can say that the rate of the reaction becomes slow. And secondly, we can control the reaction because it has three bulky groups here, and because of the presence of these three bulky groups, what we say is that because of steric hindrance, the reaction will be controlled. So we will get only an aldehyde and we will not be able to get a ketone. So if we go on to now the next reaction, then what we find here is that next reaction is the reduction of esters to aldehydes by using BAL. What is BAL? BAL is diisobutyl aluminium hydride. That is another reducing agent, which is a selective reducing agent, or which is a mild reducing agent. So what happens in this case is, so since we are having diisobutyl aluminium hydride, it will reduce an ester to an aldehyde. So now since it is reducing an ester to an aldehyde, and if you look into the structure of this reagent, what we find here is that aluminium is again attached to one hydride. So that means this reaction we will carry at low temperature, that is minus 78 degrees Celsius, and when we do the reaction with one equivalent of DBAL, then what we find is that we will get an aldehyde. Now what we have here again is, this is a strong reducing agent, but because of the presence of these two isobutyl groups here, what we find here is that it is sluggish. It has too much of baggage with it, and it does not want to continue further. That is, it does not want to reduce this aldehyde further to an alcohol. So how does the reaction proceed here? So when we talk of lithium aluminium hydride, which is a strong reducing agent, please remember there the reduction is nucleophilic. That is, hydride reacts with the carbon, carbonyl carbon. Whereas in this case we say the reaction is electrophilic. That is, this oxygen acts as an electrophile and goes and forms with aluminium, whose octet is incomplete. So as a result of which what we have is, since this lone pair of electrons are involved in bond formation with this aluminium, what we find is that this oxygen has a positive charge on it and aluminium has a negative charge on it. So in the next step what we find is that these electrons, pi electrons, will move from this place to oxygen, as a result of which oxygen will neutralize the positive charge on oxygen. At the same time, what happens is that this hydrogen as hydride will move from here and it will attack this carbon here, resulting in formation of this intermediate. Now this intermediate on hydrolysis with water will give us an aldehyde. So, and this aldehyde, if we are using, please remember, 1 equivalent of Dibal, and we are doing the reaction at minus 78 degrees, then the reaction will stop at the aldehydic stage. If we increase the reaction temperature, then the aldehyde will be reduced further to an alcohol. But normally when we are using Dibal with an ester or nitrile, what we want to do is we want to convert an ester to an aldehyde. So we will do the reaction with 1 equivalent of Dibal at minus 78 degrees Celsius when we get a aldehyde. Next method is, now what we've seen till now is that we can prepare aldehydes from acids, acid chlorides, and anhydrides, esters by reduction with mild reducing agents which are Dibal and lithium tertiary terbutyl aluminium hydride. We cannot use lithium aluminium hydride here, because if we will use lithium aluminium hydride, then we shall not be able to stop the reaction at the aldehydic stage. Reaction will go up to the alcohol. Now we have to talk or discuss special methods of preparation of ketones. We can prepare ketones from acid chlorides and nitriles. How do we do that? We can prepare them by doing reaction with organometallic compounds. So what we find here is that if we do the reduction of acid chlorides, then or acid esters or nitriles, then we are getting aldehydes. But if we do the reduction of acid derivatives with organometallic compounds, then we get ketones. So what we are doing here is, again, if we do the reaction of an acid chloride with Grignard reagent, please remember this Grignard reagent is an organometallic compound. So in organometallic compound, this alkyl will have a negative charge and this will behave like as a carbon ion, and MgX has a positive charge. Whereas if we talk of a acid chloride, then what we find is that this Cl is electron withdrawing and this oxygen here is also electron withdrawing. So this C here has a partial positive charge on it. So what happens here is that this R goes and reacts with this carbon here, and MgX goes to this oxygen. And then when we do the hydrolysis of this compound, we will get an ketone. But this is not a very good method for preparation of ketones, because we know that ketones again can react further with Grignard reagent, because this is an addition reaction. So what we find here is that R dash will come and attack here, and MgX will, acting as a Lewis acid, MgX will react with lone pair of electrons on oxygen, resulting in an alco oxide ion. And this alco oxide ion on protonation gives us a alcohol. So now what we have to do is, if we have to stop the reaction at the ketonic stage, we will have to use a weaker organometallic reagent. So now if we go back, we compare it to with aldehydes, then with aldehydes, please remember, we were doing the reaction with the acid chloride there, but we have to use a milder reducing agent to get a aldehyde, and we have to use a weaker organometallic reagent to get a ketone from acid chloride. So now if I treat acid chloride with Gilman reagent, what is Gilman reagent? Gilman reagent is dialkyl lithium cuprate. It is this reagent. So again, this is an organometallic compound, and since this is an organometallic compound, here alkyl group will have a negative charge, or it will behave like a carbon ion, and this chlorine here, this carbon here, sorry, will have a positive charge. So this will go and form a bond with here, resulting in the formation of a ketone. So how can we prepare this Gilman's reagent? So if we take 2 equivalents of alkyl lithium and treat it with cuprous iodide, then what we get here is dialkyl lithium cuprate, which is a Gilman's reagent. And this reagent now can react with a acid chloride to give us a ketone. But the question arises, how can we prepare this Grignard reagent, alkyl lithium? So please remember the reactions of alkyl halides, that if we treat an alkyl halide with lithium, it will give us alkyl lithium. So one can always say that convert methyl chloride to acetone. So what we are going to do is, in that case, we are going to treat methyl chloride with lithium, when we will get methyl lithium, and then we will treat that with cuprous iodide when we will get acetone. And then we'll get this reagent, that is Gilman reagent, and then we will treat that Gilman reagent with methanol chloride or acetyl chloride, CH3COCl, when we will get a ketone. So what we are doing here is, we have first converted this reagent as alkyl halide by doing reaction with lithium, followed by reaction with cuprous iodide. We are converting it into Gilman reagent. Then this Gilman reagent on reaction with benzoyl chloride is giving us a ketone. Next method of preparation is, we can also do the reaction of acid chlorides with dialkyl cadmium. When we do the reaction of acid chloride, again please remember, this dialkyl cadmium is what? It is again a organometallic compound. So that means this R will act as a carbon ion here. It will undergo nucleophilic substitution reaction. That is, please remember, acyl substitution, nucleophilic acyl substitution reaction, which we shall be discussing when we do acid and acid derivatives. And this will go and react here. And then this Cl, being a good leaving group, will depart from here, resulting in the formation of a ketone. The next method of preparation is, we can also prepare ketones by doing their reaction with organolithium reagents, because organolithium reagents are very reactive towards carbonyl compounds. They are so much reactive that they can react with these carboxylic acids to form a dianion. So what we find here is that when we treat this carboxylic acid with lithium hydroxide, we are able to get a lithium carboxylate. And then when we treat this lithium carboxylate with alkyl lithium, what happens here is that this oxygen, being more electronegative, will pull the electrons towards itself, and it will form a bond with lithium, resulting in the formation of dianion. Now this dianion undergoes acid hydrolysis to form a hydrate. And we know that if two OH groups are attached to the same carbon, then the molecule is unstable and it will lose a water molecule to form a ketone. So we can prepare ketones by treating carboxylic acids with organolithium compounds followed by hydrolysis. Not only this, what we find is that an organolithium compound can also result in a formation of a dianion. So what we are doing here is, that is, we are just taking a cyclohexane carboxylic acid and we are treating it with phenyl lithium. When we do so, we are able to get a dianion here, and this dianion here, again on hydrolysis, will give us a phenyl cyclohexyl ketone. This is a very good method of preparation of ketones, and we get a high yield in this reaction. We can also prepare ketones from nitriles by doing reaction with Grignard reagent. Please remember, if we were doing the reduction of cyanide by Stephen's method, that is with SN and HCl, SnCl2 and HCl, or by a Debal reagent, we would have got an aldehyde. And if we treat this cyanide with Grignard reagent, we will get a ketone. Now what we find here is that this nitrogen is more electronegative as compared to carbon, and hence it will pull the electrons towards itself. So this carbon becomes electron deficient, and this R, acting as a nucleophile, forms a bond here, resulting in the magnesium salt of amine. The question arises, we could have added a second Grignard reagent here, but we do not do so, because if we do so, we will get here N2 minus, which is not possible, and this amine now on hydrolysis gives us a ketone. So this is how we can prepare ketones from Grignard reagent also. So here what I have done is, I have done the reaction of benzonitrile with phenyl magnesium bromide, resulting in an amine intermediate, which on hydrolysis gives us a ketone. So this finishes with the methods of preparations of aldehydes and ketones. So there's another method which we can quickly go through, that if we do dehydrogenation of alcohol, that is if we pass alcohol over copper, then in that case, if it's a primary alcohol, we will get a aldehyde, and if it was a secondary alcohol, we would have got a ketone. So we'll take a break here, and in the next session we will continue with the physical properties of aldehydes and ketones. In this section, we will be discussing physical properties of aldehydes and ketones, followed by the chemical properties. So when we talk of physical properties of aldehydes and ketones, please remember formaldehyde, which is the first member of the aldehyde series, is a gas, followed by 13 aldehydes, which are liquids, and others are solids. You have to remember that formaldehyde is a gas, because normally we ask you a numerical on this reaction by giving you that compound A is a gas which reacts with NaOH to give you B and C, and you have to find out what is A, B and C. So please remember, the only aldehyde which is gas is formaldehyde. Then what we know is that lower aldehydes have an unpleasant odor, that is they have foul smells, whereas higher ones have a pleasant odor. So if higher aldehydes have a pleasant odor, they are widely used in perfume industry. Not only this, now if we look into the boiling point of aldehydes, then what we know is that aldehydes and ketones cannot form hydrogen bonds with molecules which are like themselves, that is they cannot form hydrogen bond. When an aldehyde cannot form an hydrogen bond with another molecule of aldehyde. Whereas ketones, alcohols can form a hydrogen bond, that is, they can form intermolecular hydrogen bond, as a result of which the boiling point of aldehydes and ketones is lower than alcohols of comparable molecular mass. But at the same time, what we know is that the C double bond O in these molecules, in aldehydes and ketones, is polar in nature. Since it is polar in nature, that is, carbon has a partial positive charge and oxygen has a partial negative charge. So as a result of this, there is dipole-dipole interaction between these molecules, and the boiling point of these compounds is higher than that of alkanes which are having a similar molecular mass. Now if we compare the boiling points of these compounds, alkane, aldehyde and an alcohol, then what we find is that methanol, whose molecular mass is 32, an aldehyde and an alkane, that is ethane and formaldehyde, whose molecular masses are 30, then what we find is the boiling point of methanol is highest, followed by aldehyde, and that is formaldehyde, and then ethane. The reason being the same, that methanol can form intermolecular hydrogen bonding. In formaldehyde, there is dipole-dipole interaction, and in ethane, they are non-polar compounds, so there is van der Waals interaction. The same trend is there if we compare propane with ethanol and ethanol, that is, the boiling point of ethanol is 78 degrees, followed by ethanol and propane. Now, if we talk of the solubility of aldehydes and ketones, then what we find is that lower aldehydes, in which the hydrocarbon part is less, they are soluble in water, because what we find here is, why are they soluble in water? Because this hydrogen can form intermolecular hydrogen bonding with lone pair of electrons on oxygen here. Hence, these aldehydes and ketones become soluble in water. So what we know here is that those aldehydes and ketones in which the non-polar part, that is the hydrocarbon part, is less, they are soluble in water. So what we find is, how does this trend change? So what if we find here is, now if I look into this molecule, so what we find here is that if I look into this is an aldehyde, and this oxygen here has two lone pair of electrons, so it can form an intermolecular hydrogen bond here with water as well as here with water. So this acetaldehyde molecule or this aldehyde molecule is soluble in water. Similarly, if we look into the ketone, then what we find here is, again, there is one intermolecular hydrogen bond here, the other intermolecular hydrogen bond is here, and this is again soluble in water. So what we find is that if we talk of methanol, it is very soluble, ethanol is also very soluble, but this solubility, that is in grams per 100 gram, 1 gram of aldehyde or a ketone soluble in 100 grams of water, then what we find is that propanol, 16 grams of propanol is soluble in 100 grams of water. And what we find is, if we talk of octanol, octanol is not soluble in water. So what I'm trying to tell you here is that as the hydrocarbon part increases, the solubility decreases. Similarly, what we find is that if we talk of ketone, then ketone is soluble in water to all the amounts, whereas this solubility again decreases, and 2-octanol is insoluble in water. So if we talk of the physical properties of aldehydes and ketones, then what we know is that the boiling point of aldehydes and ketones is higher than alkanes and lower than alcohols and carboxylic acids. And if we talk of the solubility, then what we find is that lower aldehydes and ketones are soluble in water, but as the alkyl portion increases or hydrocarbon portion increases, or as the branching increases, their solubility in water decreases. That is, benzaldehyde, if I talk of aromatic ketones, then benzaldehyde is not soluble in water, or it is partially soluble in water. So now we have to discuss the chemical properties of aldehydes and ketones. In aldehydes and ketones, the functional group is the carbonyl group. Since it has a carbonyl group, so it can undergo addition reactions. That is, we have a C double bond O here. So since it has a double bond here, the characteristic reactions of aldehydes and ketones because of the carbonyl group are going to be addition reactions. Why? Now the question arises, what kind of addition reactions? Since this oxygen is more electronegative as compared to this carbon, it will pull the electrons towards itself, as a result of which there is partial negative charge on oxygen and partial positive charge on carbon, and a nucleophile will attack here. Second is, now we shall see why nucleophilic addition and why not nucleophilic elimination reaction. This we will be discussing quite soon. Next reaction is, it can undergo nucleophilic addition elimination reactions. Those reactions it undergoes with ammonia and ammonia derivatives. Then what we know is that the hydrogen which is attached to here, which is the alpha hydrogen, is quite acidic in nature, and then because of this acidic hydrogen, we have special reactions of aldehydes and ketones, which are aldol condensation, and then acetone and acetaldehyde gives us iodoform reaction or haloform reaction because of the alpha hydrogen which is present here. Then we have to look into the oxidation reactions of aldehydes and ketones, and these reactions help us in distinguishing aldehyde from a ketone, because we know that aldehyde can be oxidized easily, and aldehyde undergoes oxidation reactions with Felling's reagent, Tollens reagents, whereas ketones do not do so. And then the last would be the reduction reactions of aldehydes and ketones, which we shall be discussing. So now if I look into the nucleophilic addition reactions, then the question arises that why do aldehydes and ketones undergo nucleophilic addition reactions? Because if we see, the carbonyl group in aldehyde is attached either to an alkyl group or to an H group, except in case of formaldehyde where it is attached to 2 hydrogens, whereas in ketone it is attached to 2 alkyl groups. And these 2 alkyl groups are too basic to be eliminated under normal conditions. So they cannot be replaced, and aldehydes and ketones undergo nucleophilic addition reactions. Whereas if I was talking of acid and acid derivatives, then what we find there is that the carbonyl group is attached to a weak base which can be eliminated, and they undergo nucleophilic acyl substitution reactions. Whereas aldehydes and ketones having a carbonyl group undergo nucleophilic addition reactions. Now what happens in this nucleophilic addition reactions is, if we look into the structure of this carbonyl group here, then what we find here is that this carbonyl is sp2 hybridized. Since it is sp2 hybridized, it is planar in structure. And since it is planar in structure, it is quite an open structure, that is, there is no steric hindrance, and the nucleophile can attack from either side. When a bond formation takes place here, what we find is that this goes from sp2 hybridized to a sp3 hybridized carbon here we have. So, and which is a alkyl oxide ion here, and we are going from sp2 to sp3, and then this oxygen reacts with a proton to give us a product. So what we find is that we are starting with a compound which is sp2 hybridized, resulting in a product which is sp3 hybridized. Now the question arises that if we are going from sp2 hybridized reactant to a sp3 hybridized product, what will be the rate of the reaction? Before discussing the reaction mechanism and the reactions of aldehydes and ketones, we should know which aldehyde is more reactive, or what are the factors which will affect the nucleophilic addition reactions in case of aldehydes and ketones. So what we find here is that this reaction, the rate of reaction, will depend upon the equilibrium constant. That is, if the equilibrium constant is high, then the product will be formed easily, and if it is low, then the product will not be formed easily. So if I compare the equilibrium constant of these compounds here, then what I find is that formaldehyde is very, very reactive, followed by acetaldehyde and then acetone. Why is this the case? If you look at the nature of the substrate and the product, or the nature of the reactant and the product, then we say that the factors, if the factors are stabilizing the reactant, then the rate of reaction will be slow. And if the effects, if steric effect or the other effects are affecting the stability of the product, then the product will be more formed. That is what I mean to say here is that factors which affect the stability of reactant and factors which will affect the stability of a product will decide what will be the reactivity of the reactant. So for example, if I look here, we know that if we talk of an alkene, then we say that the more substituted alkene is more stable. This also works for a C double bond O, that is, ketones are more stable than aldehydes, therefore ketones are less favorable to addition reactions. Now the question is, why are ketones more stable than aldehydes? So if I look into this structure, what we find here is that in ketones, now we've seen that this is polar in nature, that oxygen has a negative charge here, carbon has a slight positive charge here. Now since carbon has a positive charge here, so any factor which will decrease the positive charge on this carbon will stabilize the reactant. So what we know here is that in ketone we have two alkyl groups which are stabilizing or which are decreasing the positive charge on this carbon. Hence this carbon is less reactive towards nucleophile, or in other words, this ketones are less reactive. Whereas if we talk of an aldehyde, then in aldehyde this positive charge here is being lessened because of the plus I effect of this alkyl group. Whereas in formaldehyde, we do not have any alkyl groups, and this is most reactive towards the nucleophiles. Not only this, if we look into the structure of the product, then what we find is that in product, we have four groups which are close together, whereas in case of a reactant, there are three groups attached to the carbonyl carbon. Now, when we have four groups in a tetrahedral intermediate product, then what we find is that these groups are closer together, because of which there is destabilization of the product. Therefore, what we find is that the addition in ketone is less favored as compared to aldehyde. So what we find here is that when we talk of a ketone, then reactant is more stable because of the plus I effect of the two alkyl groups, and product is less stable because there is steric hindrance, because the carbon has to adjust four groups. So the delta G here is high and the reaction is unfavorable. Whereas if we talk of an aldehyde, then what we find is in case of an aldehyde, reactant is less stable and product is more stable, and hence this reaction is favored. Not only this, what we find is that if an electron withdrawing group is attached to a carbonyl carbon, it will make the reaction more favorable, because electron withdrawing groups will attract or will withdraw the electrons from the carbonyl carbon, making it electron deficient. Hence, nucleophile will be able to react very fast. Whereas if we talk of an electron donating group, then they will make the addition reactions less favorable. Now, if the carbonyl group undergoes conjugation with the group which is attached to it, then what we find is that the reaction is again not favorable. And if the size of the alkyl groups which are attached to the carbonyl group are large, then also addition is not favorable because of steric hindrance. So what we look here is, now if I compare these ketonic compounds, then what we find is that this acetaldehyde is very reactive because it has only one alkyl group. This is less reactive because it has two alkyl groups which are neutralizing the positive charge on the carbonyl carbon. Then when we look at this methyl butyl ketone, then what we find in methyl butyl ketone is that this butyl group is bulky, and because of this there is steric hindrance and it is less reactive as compared to acetone. Whereas if we talk of a tertiary butyl ketone, that is, we have a tertiary butyl group here and then we have a tertiary butyl group here, then this is unstable, first because of the steric hindrance, and secondly the inductive effect will be very high, as a result of which the positive charge on the carbonyl carbon will be highly reduced and it will not be attractive towards the nucleophiles. Now let us look into the detail of the nucleophilic substitution reactions, the mechanism of the reactions. But before we do this, let us quickly summarize that ketones are less reactive than aldehydes and aldehydes are less reactive than formaldehyde towards nucleophilic addition reactions, because as the number of the alkyl groups or as the alkyl groups become bulkier, they will destabilize the reactant. They will destabilize the product. They will stabilize the reactant through plus I effect. That is, they will decrease the negative charge, the positive charge on the carbonyl carbon, thereby stabilizing it. Now if we look into the nucleophilic addition reactions, now nucleophilic addition reactions can occur by two mechanisms. That is, they can either be base catalyzed under basic conditions or they can be acid catalyzed under acidic conditions. Now if we look into these two conditions, for this I am taking the example of water, and the addition of water to form hydrates may be acid catalyzed or base catalyzed. Now whatever the reaction is, whether it is acid catalyzed or base catalyzed, it gives us the same product, that is, it will give us a gem diol. Now what do I mean by saying it will give us a gem diol? That is, the two hydroxyl groups are attached to the same carbon, and we know that gem diols are not stable and we will not be able to isolate them, because for isolation we'll have to distill it, and when we distill this product, the equilibrium will shift towards the left hand direction, resulting in the formation of acetaldehyde. So now let us look into the reaction mechanism of these two reactions, the acid catalyzed and the base catalyzed. So whatever the reaction is, whether it is acid catalyzed reaction or a base catalyzed reaction, both the reactions are highly regioselective. Now what I mean by saying they are highly regioselective is that the oxygen will always add to carbonyl carbon atom. And in this reaction, as we've already discussed, in all the nucleophilic addition reactions, a sp2 hybridized reactant will be, after going addition reaction, will be converted into a product which will be, in which the carbon will be sp3 hybridized. Now, not only this, these addition reactions are reversible, and whether the reaction will be favorable, the hydrolysis reaction will be favorable or unfavorable, will depend on the nature of the groups which are attached to the carbonyl group. If the groups attached to the carbonyl group are electron withdrawing, then the reaction will be favorable. So now let us look into the reaction under acidic conditions. So whether we are doing the reaction with water or with alcohol or with any other reagent, then when we are doing reaction under acidic condition, these three steps are generally followed. That is, first the protonation of the carbonyl oxygen will take place, then addition of water molecule, and finally the deprotonation. Now what we find is that if I talk in acidic conditions, then this carbon, the nucleophile here is a weak nucleophile. That is, I am taking water as a acidified water, protonated water as a nucleophile here. And this water here is a weak nucleophile. So to convert it into a strong nucleophile, what we do here is that this oxygen reacts with a proton here, that is, it undergoes a acid-base reaction, that is, the lone pair of electrons on oxygen will act as a base. They will abstract a proton from here, resulting in protonated oxygen, as a result of which now this oxygen will pull the electrons towards itself, pi electrons, hence this carbon will have a positive charge. So now this carbon is nucleophilic in nature, and this weak electrophile, which is a water molecule here, is acting here as a base. In this reaction, water was acting as a proton, it was acting like an acid, it was acting like a proton donor. Whereas in this second reaction, this is acting like a weak nucleophile, and it attacks the carbon here because the nucleophilicity of the carbon has been increased because of the presence of this electron withdrawing oxygen here. And we get this intermediate. Now in next step again, water acts as a base and it abstracts a proton from here, and this goes back, these electrons go back to neutralize the positive charge on oxygen, and we get a diol here, resulting in the formation of diol. So what we have to keep in mind is that if we are doing the reaction in acidic conditions, first we have to protonate this oxygen, next a weak nucleophile will attack the carbonyl carbon, and in the last step we will do the deprotonation, resulting in the formation of a gem diol. Now if we talk of reactions under basic conditions, then what we find is that in basic conditions the nucleophile is strong, that is, nucleophile is OH minus, and we know that this OH minus is a stronger nucleophile as compared to water. So it can act directly as a nucleophile and it will attack this carbonyl carbon here, resulting in bond formation. And in the next step what happens is, now this oxygen, the lone pair of electrons on oxygen, will act as a base and they will abstract a proton from the water molecule in acid-base reaction, resulting in the formation of a diol. So what we have here is, whether we do the reaction under basic conditions or we do the reactions under acidic conditions, the net result is addition of what OH group to the carbonyl group, carbon. But these diols are unstable, and when we try to distill them, the equilibrium moves towards the left-hand direction. But if what we observe is that if a strong electron withdrawing group is attached to this aldehyde group, that is, if I have chloral here, that is trichloroacetaldehyde, then these three chlorine atoms are electron withdrawing, and what we get here is a chloral hydrate. And this chloral hydrate is stable and it can be isolated. The question arises, why is it stable and how can we isolate it? We can isolate it by distillation, and it is stable because what we observe here is that there is intramolecular hydrogen bonding between the chlorine and the hydrogen atom here. Here is a intramolecular hydrogen bonding, and again here we have a intramolecular hydrogen bonding. As a result of this chloral hydrate is stable. Now what we have to talk of is, if we talk of a next addition reaction, which is addition of HCN. So if I talk of addition of HCN to an aldehyde, which is acetaldehyde, then what we find is that this reaction will take place in a basic medium. So what happens in basic medium, this HCN ionizes to give us a CN ion, which acts as a nucleophile, and it goes and forms a bond with this carbon, resulting in a tetrahedral intermediate, which then reacts with proton to give us this compound, which is 2-hydroxypropane nitrile. If you look into this molecule, I would like you to observe one thing, that this molecule is achiral. Whereas when we do the reaction with HCN, we get a product which is chiral. So I leave this for you to find out why is this happening, and we shall discuss it in the next lecture. But before I wind up, so what we know is that in slightly basic medium, it is the cyanide which acts as a nucleophile, and then that is, it is acting here as a nucleophile, then which gives us an alkyl oxide, and on protonation we will get the product. So I have left the question to you, which we shall be discussing in our next lecture. Thank you.
Thank you, ma'am. Friends, we will be having more such valuable sessions in the upcoming days. Till then, thank you and goodbye.